does not look anything like 1 by root t or 1 by t type of step sizes. They typically look like constant, and they can have some funny schedules. That is, it will be constant for let's say 50 iteration. Then after 50 iteration, I will drop it down to say half of that constant, and so on. Which does not look anything like the step size that we are sort of prescribing in this classical analysis. Typically, we use larger batch size rather than this batch size of 1. And that tends to have some impact on our performance of the algorithm. And then finally, we use like practical SGD with some sort of momentum term or some sort of accelerated techniques to get faster rate of convergence, whereas this classical analysis of SGD was without any momentum term, that is, there was no acceleration, so to speak. Right. So these are sort of various differences. All these differences are sort of critical. Like if you sort of try to use just the standard analysis and standard version of SGD, it does not perform as well for your deep learning system. So these changes must be doing something interesting. And in this talk, I will just discuss how sort of, we can analyze several of these changes, several of these subtle differences. And in fact, when we do this analysis, it also gives us a little bit more information on how we can sort of, go back and change our SGD methods also, like that we are using for deep learning, and maybe make them even better. Right? So let's first look at like the biggest sort of difference here, which is convexity versus non-convexity. That is, we are like classical SGD was sort of designed for convex functions, I would presume, but it is applied very easily to non-convex functions. For non-convex functions, like even if you find a point where the gradient is 0, it can have sort of function value which is really suboptimal, right? And now, one question that you can ask is that, like, at least using a gradient descent type of method, it seems very unlikely that we will get to the global optima of this function. Can we at least get to a local optima, right? So the local optima of a function is defined as a point w, where in a small vicinity around w, the function value is always smaller than any other point in that vicinity, right? Unfortunately, finding local optima itself is difficult in general, like it is an NP-hard problem. So we can sort of maybe bring down our expectations on what we can expect SGD to do. Maybe we can hope to get some sort of first order stationary points of our function. So first order stationary point are defined precisely to be the quantity that SGD is trying to optimize. That is, if you find a point w such that the gradient of your function is equal to 0, then that's called first order stationary point, right? And like intuitively, any gradient descent method is trying to find such a point. So hopefully SGD solves this problem. Let me sort of dwell a little bit more on this first order stationary points and why they need not imply your local optimality, why they might have some sort of issues, but still, like they are reasonable sort of tools to study in practice. So first thing, why they do not imply any sort of local optimality, right? So if you consider a very simple function like this, that is, it's a function of two coordinates or two variables w and w2. Is given by w1 square minus w2 square. You compute their gradient. Gradient is given by w1 and minus w2, right? Now at point 0, 0, that is when w1 is 0 and w2 is 0, right? The gradient is exactly equal to 0. So it's a first order stationary point. But when you look at your Hessian, it is indefinite, right? Which means that this point cannot be a local optima. It cannot be a local minima. And in fact, when you compute the function value at any point, like let's say epsilon by 2 comma epsilon, where epsilon can be arbitrarily small, the function value will turn out to be something like epsilon square times 3 by 8, right? So with a negative sign. So in a very close proximity to 0, 0, no matter how small sort of area that you cover around 0, 0, you can find points where the function value is strictly smaller than the function value at your first order stationary point. Okay. I also want to sort of you to sort of look at this thing, which is that sure, the function value is smaller, but it is smaller by this value of about epsilon square. right? And I'll sort of generalize this fact in a couple of slides. Now you can say that okay, here the issue was that my Hessian was indefinite. So maybe I will go for second order stationary points where I will want my W to be W to have Hessian, which is positive semi-definite. So you want to find a point W where the gradient is equal to 0, that it is a first order stationary point, but on top of that you want the Hessian to be positive semi-definite, right? So does the second order stationarity imply local optimality? Any answers? Yes? Any no's? Actually it does not. So let's take an example. You need strict positive definiteness. If it is greater than equal to 0, that is if some eigenvalues, if they can be 0, it can create an issue, and we'll just take an example. So let's say if you look at a function like this, again it's a two variable function. You compute your gradient, it looks something like this. You compute your Hessian looks something like this. So this is a third degree function, right? Now at 0, 0, your gradient is equal to 0 and your Hessian is equal to 0. That is, this is the point, right? And here, like you can easily see that it is not a local optima. And just to be more precise, if you compute the function value at epsilon, epsilon, where epsilon can be whatever small constant you want, the value turns out to be negative. It's minus epsilon cube times 2 by 3, which is less than the value that you have at 0, 0. So just second order stationarity is not enough. But what, like at least this example is showing that my function value is bounded by epsilon cube at least, right? And this is something that you can generalize. That is, if you have a first order stationary point, then within a small ball around W, you can bound the function value by W minus, there is a typo, W minus W prime square. Similarly, if you have a second order stationary point, in again a small ball around W, you can bound the function value by this additional term, right? And that's why you can easily see that if you want to get a local optima, then you better go to infinite order stationarity. That is, if you have p is equal to infinity, then you get precisely the local optimality condition, right? Now, so this is good, but can we really achieve this local optimality? Unfortunately, we cannot even get to a stationary point of degree greater than equal to 4. That is, we know how to get to a first order stationary point, second order stationary point, even a third order stationary point with some reasonable algorithms like polytime algorithms. But beyond this, the problems are NP hard, and in general, local optimality is a pretty hard problem, like it's an NP hard problem. But in practice, stochastic gradient descent does work well. That is, you can sort of see that in most functions that you will see in practice, if you initialize randomly and apply stochastic gradient descent, it converges to a point which looks like a local optima. So it works well, but we do not know what will be the rate for it, what type of functions can we characterize for which SGD will get to local optimality. These questions are still open. Yeah, that is, if you are somewhere here now, like, and if you are taking steps only according to the gradient, then it's very difficult for you to figure out what direction should I go in, because yeah. Sometimes you will need to, that's not necessary. Like even if my entire landscape has just these valleys, but if I'm flat in certain directions, at some positions if I'm flat, then SGD doesn't know how to move at all there, and that's sort of the main issue. But typically what happens is that when you initialize randomly, or let's say if you have multiple random initialization, your chances of getting stuck in those type of situations tends to be low, at least for practical functions. Again, you can construct some theoretical functions where you'll get stuck for sure. Yeah, this is with probability 1, but we do not know any rates here. So this works. Sorry. Yeah, this is with probability 1, but this works only when your step size is infinitesimally small. So you might actually take exponential amount of time to get to that point. All right. So let's first talk about finding this first order stationarity and if the stochastic gradient descent works for it. The short answer is yes, that is if you apply your standard stochastic gradient descent, and if you assume, like, because we are talking about first order stationarity, then it means that the gradient at least should exist. If the function is non-smooth, that is if the gradient doesn't exist, then you have to play more tricks. You have to sort of smoothen the function out and then talk about first order stationarity. But here, let's assume that the function is smooth, then it's very easy to show that stochastic gradient descent will converge to first order stationary point at certain rate. Again, the proof is like just 3 lines. This is your smoothness condition, and now, so this does not use convexity here, right? This is just smoothness, and then here you use the fact that that this Wt plus 1 minus Wt is essentially the gradient at that point of one of the function which is bounded by g, and again you replace this quantity by the expected value of Wt plus 1 minus Wt times eta, or 1 by eta, sorry, and that's it. So you get this, you again sum it over all the iterations. Now you can only claim something for the minimum over the iterations, that is over t iterations. My value of the gradient at some point during the set of iterations, that will be bounded by this quantity. Average does not make sense because if you take an average, because it's a non-convex function, your function value might be actually larger. So you have to find some point where the gradient is minimum. Yeah, you can guarantee it for summation of, let's say, f of Wt or summation over gradient of Fwt. And then you have to choose it randomly or you choose the minimum one. Yeah. Simulated annealing is going to go in a different direction, right? That is, if I want to climb up some of my hill to get out of the first order stationary point, then I should do simulated annealing. But here we are saying that I'm happy to converge to first order stationary point. How does SGD work? What is the rate of convergence for SGD?
Close to first order stationary
yeah.
OXP, the way you
yeah.
it, in terms of the value of the gradient, not necessarily maybe approximation of the point itself, but that would require you to be.
Yeah. Yeah, that, but the gradient is Lipschitz for us, so that's okay. Yeah, so the distance can be very large, so that's why we can only try to define it in terms of the gradient value itself, that if my gradient value is less than equal to epsilon or not. Yeah, you're right that finding exact first order stationary point, that's also challenging, but you want to find approximate one which is where the gradient is reasonable, right? And here, like, after you do all this calculation, what you essentially get is that the rate of convergence is now like t to power 1 by 4 rather than t to power 1 by 2. That is, for this problem, if you apply SGD, your rate of convergence is something like 1 by epsilon to the power 4. When you are using convexity, your rate of convergence is 1 by epsilon square. So you have to pay this extra price for applying SGD to non-convex functions. And here you are not converging to global optima or local optima, you are converging only to first order stationary point. Now people have come up with these different methods and different analysis to speed up convergence to first order stationary point, like you can have an accelerated gradient method for this, you can have a stochastic variance reduction based method for it. But unfortunately, like so far we have not seen usage of these methods for training deep learning solutions. Somehow those methods, like they do not seem to work very well. So SGD has a lot more sort of tricks up its sleeves, it seems, right? Okay, so now let's talk about second order stationarity. Can we have some stochastic gradient descent type of methods that converge to the second order stationary point? And here again, answer is yes. Now, getting to exact second order stationary point, that's difficult, but let's talk about converging to a approximate second order stationary point. That is, you want to find a W where the norm of the gradient is less than equal to epsilon, and the Hessian at that point is like its smallest eigenvalue is bounded by something like minus root epsilon times this approximation factor rho. Right? So this, like if you can find a pair, this will be called an epsilon comma rho pair. for approximate SOSP. All right, so this is again sort of a very well studied problem, and like if you use some classical methods like the cubic regularization method, then you can converge to a second order stationary point in a pretty good time, like 1 by epsilon to the power 1.5. But this method is not practical at all because it needs you to compute Hessian of the full function, which is out of the realm of possibility in deep learning and these standard machine learning tasks. Now, you can use some sort of stochastic gradient descent with some noise to solve this problem. That is, what you do is you do your stochastic gradient descent till you converge to a first order stationary point. After that, you add little bit of noise so that you perturb yourself, and if you are at a bad sort of first order stationary point, if you are at a stationary point which looks something like this is also a stationary point, right? Well, generally you will not get there. But let's say if you are getting here, if you do this perturbation here, you will then converge easily to, like, you will sort of bump down and you will go to a better point, right? So here for analysis, we are adding this extra noise, like artificially. But what happens in practice is that because you are doing SGD already has some noise inbuilt, right? And that noise itself serves as this perturbation that can help you then deviate from this first order stationary point and go to a second order stationary point. All right, so like pictorially how it looks is that suppose you start at this point and you keep on doing your gradient descent or stochastic gradient descent, maybe you'll get to this point. But now at this point, if you do perturbation, then you go in this well of second order stationarity and you will just go to a second order stationary point. I will not go in the analysis here, but what you can show is that using the stochastic gradient descent with the noise, you can get to second order stationary point in 1 by epsilon to the power 4 iteration. Again, there is a lot of work to improve this convergence to second order stationarity based on some sort of noisy gradient descent, accelerated gradient descent, stochastic variance reduction methods. But again, SGD is the method that we use in practice. These other methods have not been able to make big dent, which also sort of indicates one thing, which is that maybe for these deep networks or for machine learning problems with these non-convex functions, maybe we are not just interested in second order stationarity or first order stationarity, etc. There is some more property of the optima that we are looking for that SGD is able to serve, which we do not understand very well so far. Yeah.
So right now, you were saying put the noise when you test the first order condition.
Yeah.
But the SGD is having noise everywhere.
Everywhere, yeah.
Same convergence rate.
You will get same convergence rate, but you will need to make some assumption on the noise that SGD is adding in each iteration. In general, like you have to sort of, like, if SGD, the type of noise that SGD is adding, it's only in like one direction, then this does not work. So you have to explicitly make that assumption that somehow the noise has some component in each of the direction. So that algorithm works with infinitesimally small step size, but we do not know any rate of convergence for that. So if you want to get a finite like this sort of poly or pseudo poly time rate of convergence, then we have to explicitly add noise either through SGD step itself or by adding some explicit noise.
So explain why gradient descent would get stuck, potentially get stuck, and so we need to add noise. Why is it the case that SGD might get stuck? Why do you need to add noise to SGD?
That's precisely what I'm saying, that intuitively you should not require to, but so far the analysis requires, because the noise that SGD has, that is, so the type of noise that SGD has is the following, right? Like it's grad FIT W minus the actual gradient, right? This noise need not have component along each of the direction. So it might be concentrated in only maybe one direction, and that one direction does not have any slope, so you are in trouble. So you have to sort of add this assumption that either the noise has component, like this particular noise has component along each direction, or you add it explicitly. But you're right that in practice we have never sort of again observed that SGD does takes really long time to converge if you do not take this explicit noise. It does not happen like that. So so maybe at least for some class of function that we are interested in machine learning, maybe there is something more that we can exploit to ensure that SGD without any explicit or additional noise converges. All right. So, so this was sort of the story for convexity versus non-convexity that at least I know so far, which is that SGD is able to find some of the standard notions of optimality in non-convex optimization literature, like first order stationarity, second order stationarity, but still it does not solve the problem completely. I believe because for those problems, we have been able to design much better algorithms whose rate of convergence is much better, but still in practice what we observe is that SGD's performance is better. So there's something more to the problem, and yeah, it would be good to sort of figure that out sometime soon. So now let's look at the another aspect that I was harping on when I was talking about practical SGD versus the classical SGD, which is that classical SGD will assume some sort of averaging of your iterates, whereas in practice you just use the last point, right? So can we understand why just the last point itself works, and what is sort of the literature so far? So, so for last point, if you assume just a general convex function, general Lipschitz convex function, it's known that the rate of convergence that you'll have will be 1 by root t. I'm ignoring other constants. Let's just focus on t itself. This is a information theoretic lower bound. So obviously we cannot do any better than this. But so far, using standard step sizes like the step size of 1 by root t that I talked about, the techniques that we know of get you only log t by root t rate, whereas if we took an average, we would get a rate of 1 by root t. So at least this result says that we should take an average, right? We should not just use the last point. And furthermore, it's not like this proof is not tight, and that's why we are getting this log t rate. For the standard step sizes, there is a lower bound which says that you cannot do any better than this log t by root t. So you have to pay this log t factor if you want to use the last point of SGD, or even actually standard gradient descent for general convex functions. But what we show in this work that we presented at this computation, conference on learning theory this year was that if you come up with a new sort of modified step size, then you can actually get a rate of 1 by root t. So you can get your information theoretically optimal rate if you are using some modification of the step size, right? So let's look at that modification, or let me first sort of give a little bit of intuition of why the standard rates struggle. So let's consider this very simple function, which is just mod of x, that is, it looks something like this. So here what happens is that even if you start very close to the optima, because the function is non-smooth, even at the optima, like or very close to optima, your gradient can be large. It can be like, for example, here for this function, if you move in slightly from 0, your gradient becomes 1, right? So you have to set your step size to be small to then converge, but then if you set your step size too small, then you are never going to converge. That is, when you are starting far away, you will just sort of stay in this region only. You will never get to this point. So because of this, what happens is that these methods, they will converge up to some point, and then they will keep on just oscillating without getting to the optimal solution, right? But if we change the step size, then we can resolve this issue. So the step size change that we have is the following. So for the first t by 2 iterations, we use the standard step size of say 1 by root t. Here I'm hiding all the constants of the gradient and diameter, etc. Right? Now for the next t by 4 epochs, we use the step size which is half of that step size, because here we have already done majority of work. That is, we have already got a function value to be very small, and now what we are saying is that let's just go and settle down. So the way to do that is that we will use a smaller step size, so that we do not sort of oscillate in a big area. We hopefully will start oscillating in a much smaller area around our iterates here. And then for the next t by 8 iterations, we will use a step size which is even half of the earlier step size, that is a step size of say 1 by 4 times root t and so on. So we will keep on halving our step size for the next half of the iterations, which means that finally, like in the final sort of epoch that we have just one point, and there the step size will look like something like t to power 2 to power minus I think log t by root t or so, right? So really step size at the end, okay? And for this step size schedule, what we can show is that with very high probability, like probability 1 minus delta, the last point of this SGD method will be good. That is compared to W star, its excess error is just 1 by root t, right? So we can get the clean result that we get for the average iterate in general, right? If we look at our proof, like the intuition for the proof is that already in first t by 2 iteration, we would be reasonably good. We would have got a rate which is like something like, so let's say root 2 by root t, right? Now all we need to make sure is that we do not move move too far away from this point. And for that, what we sort of say is that, okay, we will, in each of these epochs, we'll find out a point which is minimizing the function value, right? And then we can sort of get this general identity, that is the function value that I have here in this epoch, like the minimum function value in this epoch, is not much worse than the function value that I have in this epoch, right? And that's why the final function value that I'm getting, it is not much worse than the already like 1 by root t rate that I had. So I will get overall 1 by root t rate. So you can sort of extend this analysis to the case when the function is strongly convex, that is when f of w is strongly convex. There the step size that will be setting will be 1 by t, then half of 1 by t, 1/4 of 1 by t, and so on. And again, you can get a rate of 1 by t, which is again sort of equivalent to standard or classical SGD's analysis for such functions. That's a great question. Our conjecture is that you cannot do that at all. That is, here to set this step size, we need to know the horizon. You need to sort of come and tell me that this is the final accuracy I want, from which I will calculate the number of iterations I should run, and that will then determine my step size. But suppose I tell you that no, I don't want to sort of give you this horizon or the accuracy a priori. I just want you to run the algorithm forever, and I can stop the algorithm at any point of time. And at that point of time, like for the number of iterations that I've run, I should get accuracy according to that. Unfortunately, we do not know of any technique to be able to do that. That is, we do not know any time algorithm that will have a rate of 1 by t or 1 by root t for the last iterate. And our conjecture is that you cannot do that at all. Like, it is hard to get such a rate, such a step size, which will ensure 1 by t rate for any time algorithm. Yes, continuous time analysis. For any time algorithm, no, I don't know that either. Yeah. So yeah, in continuous time analysis or in discrete time, any time algorithm which has 1 by t for the last point or 1 by root t for the last point is an open question. All right. Any other questions? Okay, so this is sort of just an illustration of what happens when you apply our method, that is our step size schedule to this problem. We observe that the algorithm is able to converge to better solution in same number of iterations, right? And because of this, now you can apply it to solving support vector machines. Support vector machines are very sort of, at least till 2010, they were sort of the way to go for solving your standard classification problems, and they use loss function which is non-smooth, right? Which means that now you cannot sort of, either you have to do some sort of averaging, or your last point is not going to perform very well. So this is the curve that you get if you are doing the averaging. right? So this looks very smooth. This is fine in terms of loss function. So this is number of iterations. This is the loss, and this is how the loss looks for your averaged version, which looks good. Now, if you look at our method, it is able to get to like pretty much the same value as the average version. In fact, it is going even slightly below. Whereas if you apply standard method, then it is not able to get to that small error, right? And this is slightly more smooth curve because we average it over 100 runs of SGD.
Is this the suffix averaging of the standard method or the suffix averaging of your?
Of standard method.
Get anything better by suffix averaging your?
No,
Like,
because
practically,
already,
not the
yeah.
rate, not the rate, but practically.
Practically, we have not tried, but I really doubt if we'll get anything better. But yeah, maybe we should try it out. Okay. All right. So before lunch, let's look at one more key difference between theory SGD and practical SGD, which is sampling with replacement versus sampling without replacement. As I said that it looks like a small difference, but it is really critical difference. If you use sampling without replacement, with replacement in practice, it does not work very well. Plus, it is harder to implement it because imagine that you have your data points spread across large disks. Now, if you are doing sampling with replacement, you will need to do random access in each iteration, which is very, very difficult. Whereas if you are doing sampling without replacement, then you can have just one permutation or one layout of your data, and you can just go sequentially over the data one by one, and so because of that, implementation becomes much, much easier, right? Now, so how does this sampling without replacement algorithm looks? Well, you run for some k epochs, right? Now you do not have just iterations, you have some epochs over the entire data. In each epoch, you sample some random permutation over your data points or over your functions. And then in each iteration, you pick the function according to your permutation, do standard like stochastic gradient descent type of update with some step size. And then once you are done, you use the last iterate of this epoch as initialization for the next epoch. And you just iterate like this. So for any questions for the setting? So for this problem, the funny thing is that if you just assume the standard setting, that is, if the function is convex, it is Lipschitz, not smooth, sorry. If it is just convex and Lipschitz, then we did not even know if this algorithm will converge to the global optima or not. That is, will it converge to our desired solution or not? We did not even know that, right? So in this work, what we show is that yes, we will converge, and we will converge at rate which is very similar to the rate that you get for SGD. So here k is the number of epochs, and n is the number of updates that we are doing in each epoch. So the total number of iterates or total number of updates that we are doing is equal to nk. So the t that I was using earlier is equivalent to nk here. So we are getting 1 by root t rate under exactly the same set of conditions. Now, if your function is strongly convex, then we can get a rate of which is like same as 1 by nk. And furthermore, if the function is Lipschitz and it is smooth and it is strongly convex, and the number of iterations that we are running for is large enough, I will come to this large enough part later, then actually the rate of convergence is even better. We can have a rate which is 1 by k square, which is strictly better than what SGD gives you. SGD gives you only 1 by nk, but we are able to get 1 by nk square, which seems somewhat surprising that here it seems like that this method was harder, or this method was doing something incorrect because it was not sampling with replacement. But in the end, this method is actually working faster if your function is smooth, it's Lipschitz, it's strongly convex, right? So, so what's the intuition? Why does this happen? Why are we getting faster rate by using this method? So I won't be able to go in exact detail, but sort of one simple intuition that I find useful is the following: that suppose you are already at your optimal solution W star, right? Which means that your gradient is equal to 0, right? But that does not imply that gradient of every sub function here that you have is equal to 0. In fact, gradient of fi W star can be non-zero for all I, right? and still your gradient of FW star will be equal to 0. And in fact, that's what will happen in practice, like even for these SVMs, etc., that you apply this method to, your gradient with respect to each point is going to be non-zero, but the summation is going to be 0 or very close to 0, right? Which means that even at W star, when you apply SGD, you are going to move significantly because your gradient for any single point or any single function is not equal to 0. But now when you look at the random permutation or random reshuffling based SGD, that is SGD where we are doing sampling without replacement, there the gradient with respect to this random permutation is equal to 0. That is, at W star, no matter what random permutation I take, the gradient is going to be 0, right? I mean, this is just another way of writing summation over I, Fi, gradient of Fi W star. I'm just permitting my functions. So that sort of gives you an intuition that it is doing some sort of variance reduction. That is, if you are very close to the optima and your step size is small, reasonably small, then you do not move a lot. Like your entire variance in your updates is fairly small, and that leads to this faster rate of 1 by k square that we have. Right? So now, how do we put it in practice? Like put it in a proof. So as I mentioned, that sort of main issue in analyzing this method is that my expectation over individual function is not equal to the expectation of the gradient for the entire function, right? Like this is the update, this is the function that I'm using, or this is the gradient that I'm using to update and iterate. And when I take expectation of this is not going to be equal to my actual gradient, right? This held true when I was doing SGD with replacement, but SGD without replacement, this does not hold true, right? But what I do know is that suppose I was doing updates with some permutation, but there is another permutation sigma prime which is independent of that sigma, then in that case for every step this expectation holds. I mean, this is again a trivial statement, right? My W is not at all dependent on sigma prime, so that's why, and sigma prime is a random reshuffling of data for my functions, and that's why this expectation holds. So now the idea is that we will somehow tie in these two things. That is, we will say that expectation of my function or of my gradient with respect to this permutation is actually equal to the actual gradient, but with some small error added on top of it. This small error is given by the Wasserstein distance between W that I'm getting by the sigma permutation and W that I'm getting from, let's say, some other permutation. It's just bounded by that Wasserstein distance. And sort of the main point of the proof is that we can show that this Wasserstein distance is bounded as long as certain conditions are satisfied. And we can bring all these things together to get this final result, right? So this final result, what it says is that if the number of iterations that we have is larger than the condition number square of the problem, condition number is of a optimization problem is the smoothness parameter divided by the strong convexity parameter. So if we are taking iterations which are this large, then we observe that you will have a 1 by k square rate of convergence. Similar results were already sort of known in the literature, but those results required an additional condition, which is that they needed the Hessian of the function to be smooth as well. Whereas here we are working with the standard set of assumptions. We do not require anything more than the standard smoothness and standard strong convexity assumption.
Would you have grid replacement in the beginning and towards the end bring in without replacement and achieve the rate?
That's pretty much the proof idea that is used to get this rate. Like so, there was some work by Ohad Shamir which get this rate of 1 by nk. He used pretty much the same idea. He said that most of the work is done in initially, and the later iteration just does not spoil it too much. So that line of attack cannot give you faster rate. It can only sort of say that I will be at least as good as standard stochastic gradient descent with replacement. But here what we are saying is that no, you are somehow reducing the variance, and that's why you should get better rate. So that's sort of the difference in philosophy.
But I'm saying that towards the end you do use the without replacement, so you do get a range reduction.
Yeah.
And you do get the rate of without replacement.
We do get rates, yeah. Yeah. So this 1 by k square is precisely due to sampling without replacement.
Later on you do without replacement.
No, we do not do anything like that. We just do random reshuffling.
If you do it that way, can you still achieve the ratio?
Yeah, you will, because for, like, you can sort of say that for initial, say 90% of the epochs, anyways the two distributions are almost the same. And like in TV distance itself, total variation distance itself, the distributions will be same. The main sort of thing happens in the later part. That's where the variance reduction is. So yeah, probably you should be able to get the same.
So, I guess if you ran gradient descent, you would only need kappa log 1 by epsilon iterations to get to an epsilon accuracy, which is n kappa log 1 by epsilon gradient call.
Yeah.
So isn't kappa square, like if that you never ever run SGD for that many epochs, right? Because if you had that budget, you would just run GD.
Yeah, that's a great point, that still this result is weak in this sense because we require too many iterations, right? And in fact, if the function is smooth, strongly convex, then in general, there is no reason why you should actually do SGD at all. You should probably do GD. But in next talk, like this is a very good segue. There is a next talk, I will sort of give you an example where actually you would want to run SGD even when your function is strongly convex, smooth, etc. And that's because the function has some sort of nice stochastic properties. Okay. All right. Yeah. Sorry, recent work on?
The idea is that we study gradient flows in the space of entropy.
Yeah.
There's an algorithm which uses addition of time.
Yeah. So we are, that's a great connection, but at least we are not using those proof techniques. There, at least my understanding is that, yeah, you talk about continuous flow. And when you are talking about this continuous flow, then you can write the whole thing as just some partial, like some sort of PDs. And those PDs are much nicer to analyze. You can analyze them very easily. And then you can, when you need to discretize to get your final algorithm, when you're doing this discretization, you need to talk about this Wasserstein distance. But here, I'm not sure if those techniques are useful. What we are saying is, if you have sort of two permutations, and you are doing two independent runs with those permutations, then what is the difference between, or what is the distance between the distribution of our iterates? And what we are saying is that the distance is not going to be too large. So you will be fine like running with either permutation. Okay. Yeah.
Just maybe out of curiosity. So when you look at the proof for SGD, that's sort of an entrepreneurial online part and an expectation part.
Yeah.
And I'm wondering if your result can be phrased as sort of a weighted regret statement, plus taking expectations on top. So the weighting would be that the last rounds are getting sort of exponentially heavier, and you take a random sample but with weight, so you always take the last one.
That's a great point. Yeah, that, so you're saying that I will do my online convex optimization or online GD with this step size, and then do a batch to like this online to batch conversion kind of trick.
Increasing the weights of the rounds as you go in time.
Go in time.
And then you average with those weights instead of uniform.
Uniform. Probably, yeah, I think that should work out. You are right. Yeah, I think, let me think through this. So probably it should work out. You are right, because like what we will need to sort of work, make sure this works out is the following, that like the way analysis is working is, here I have some minimum, here I have some minimum, here I have some minimum in these epochs, and I have to somehow relate them. I have to say that I cannot get much worse, right, during these epochs. So what we'll need to do is maybe online to batch conversion here, online to batch conversion here, online to batch conversion here, and get the minimum, and then we will have exactly the same relation. So maybe.
But not for SGD, still for the decaying step size.
For decaying step size SGD.
You won't just get it by taking SGD and doing a different method.
No, but you do SGD where you put a weight factor in every round.
Yeah, but you're saying to the same step size.
If you tune the step size, knowing those weights, it will come out to be a spectrum like this.
Probably, like that sounds reasonable, but yeah, we'll need to think more. Okay, all right. Any other questions? Okay, all right. Thank you so much.
Okay, let's hang for this. Not bad. I guess we meet at 2 o'clock.
Yeah, I saved 7 minutes.
Lunch you can follow us. It will be near your building. There is so much security that it's probably safe to leave our stuff behind.